Here's an intriguing experiment. The cannon on this train is pointing vertically upwards. When a ball is fired from it, it goes straight up and straight down. But what would happen if the cannon was fired when the train was in motion? Will the ball land near the cannon, or behind the train, or where? What do you think? Well, it lands more or less back on the cannon.
Maybe that experiment surprised you. Many of our intuitive ideas about motion are wrong, and yet they were embodied in the theories of one of the greatest thinkers in history, Aristotle. He lived in Greece in the 4th century BC. He was a pupil of Plato and tutor to Alexander the Great.
Do you still consider the universe illogical? Does not nature enjoy simplicity and go about its business by means of laws every bit as rigorous as those which govern the affairs of men?
Then what law, Master, decrees that a stone hurled into the air must always fall back down to earth?
Excellent question. And here we have a stone to provide you with an answer. See, it sits on the floor, immobile. Now, why is it motionless?
Because it has nothing to make it move.
Correct. It is in its natural state, at rest. Only if I force it to move, so is its natural resistance to movement overcome. When I cease to exert an influence, it ceases to move. In other words, for a stone to be in motion, there must be a reason, a cause, a force to persuade it to move.
For the stone to rise into the air, I must provide the force to lift it.
Just so.
And yet, when I let it go, it falls without any prompting from me. I applied no force to make it move downwards, did I?
Look all around you, Alexander. Do you see any heavy object that is not resting on the ground?
No, Master.
That is because all heavy objects naturally exist on the ground. Though you might perform a violent action in raising that stone, it will always try to return to the ground where it belongs. As soldiers sent to battle yearn for home, so a stone raised in the air will want to return to its proper place. That tendency in itself is a force of nature, whereby all heavy objects will take the most direct route back to the ground by falling vertically downwards.
I comprehend.
Good.
Master, might I ask, if I were in a chariot drawn by 4 strong horses, and I raised a stone above my head and let it fall, would it land at my feet in the chariot?
Is your chariot moving at speed?
Oh, yes, like Phoebus's chariot charging through the heavens.
Well, your stone would fall vertically, taking the straightest route to the ground, while your chariot moves forward, away from the direct path of the stone. In consequence, the stone would fall behind the chariot. Why, in the time it takes for your stone to return to its natural place, your chariot would have sped on many paces. It is the same as if you let fall a stone from the mast of a ship. If the ship were moving fast over the sea, the stone would plunge into the waves behind it.
Yes.
There is no need for experiment when the logic is impeccable.
So then, Master, what is there to stop the moon from falling to the ground?
The moon?
Yes, and the same goes for the sun and the stars. Why do these heavenly bodies not fall towards us?
I have heard it said that the Celtic tribes believe the sky will fall on their heads. Have you been speaking to these savages?
No, Master, but I am unsure of how to think of these matters. There are philosophers who say that the earth travels in a great circle and the ground we are standing upon is moving.
Alexander, who is your tutor? Me or those charlatans?
You, Master.
Yes, I, Aristotle, standing upon my solid ground, while you, Alexander, standing on your moving ground. Do you experience any sense of giddiness? Do you fancy the whole world is flying around in a great circle?
Well, no.
Well, no. If the whole earth were in motion, what would happen to the birds of the air? They would get left behind as soon as they left their perches. And if I were to throw that stone into the air, with the earth moving and me upon it, why, the stone would come down on the far side of the Parthenon. Which is why this whole notion of a moving earth is so patently silly. I forbid you to entertain such freakish ideas. The earth is in its proper place, at the center of the cosmos, and the ground we stand upon is still.
I believe you.
At last.
But what about the moon?
Oh, the moon.
By all your laws of motion, the moon must fall to the earth if there is no cause or force to hold it in the sky.
Is it heavy?
The moon, I cannot say.
I think you can. Logic, Alexander, logic. If the heavenly bodies were as heavy as earthly matter, they would fall. Yet they do not. Conclusion. The moon is made of a substance vastly different from that of a stone. I have called this substance ether. Ether. Such a good word.
So, Master, according to your laws, the natural place for such bodies is in the heavens.
Of course. The moon has no tendency to fall to the ground. The same applies to the sun and the stars, and everything is in its place.
Then, if a man could sprout wings and fly to the moon, he could not stand upon it.
I do not think that standing upon the moon would be very good for the moon or for the man. Let us put these speculations aside, Alexander. You have worlds enough to conquer here on Earth without dreaming of the moon.
Aristotle was convinced that the Earth is stationary. It feels stationary, and things don't get left behind when they're thrown up in the air. But then neither did the ball get left behind on the moving train. So Aristotle's ideas were not correct. Yet, for centuries, his theories were generally accepted. It wasn't until the Middle Ages that people began to seriously challenge his world system. Galileo Galilei, in about 1600, made one of the earliest studies of the moon and the stars using the newly invented telescope. This gave him a radical new perspective on the universe, but it got him into terrible trouble with the authorities.
Your thoughts, Signor, are heresy.
The truth is the truth. Is the Mother Church so fearful of science? Our Earth behaves as do all the wandering stars. I have observed that there are 4 moons that circle Jupiter in orbits of their own. So does our moon circle the Earth, as the Earth describes her orbit around the sun.
Oh, you are deranged. If the Earth were truly spinning round the sun, surely we would feel this ceaseless motion. The very air we breathe would be snatched away from our lips, and a ball thrown upwards would vanish over the horizon.
No, it would not. I have explained, and I have proven.
Proven, Signor?
Where do I begin? A ball falling from a great height will fall faster and faster until it reaches the ground.
Why faster and faster?
There is a gravity which pulls the ball downwards. The speed of its fall increases in proportion to the duration of the fall. In my experiments, I have shown that all bodies fall at the same increasing rate. That is vertical motion. But I can also make a ball move horizontally.
Sideways motion.
Sideways motion. Give me a plank of infinite length, smooth and horizontal, and could I but remove all impediments, this marble could roll along that plank at a uniform speed forever.
Without an external force to keep it in motion? Oh, come now. Nothing is eternal but the maker of all things.
You have been sent to trap me.
Oh, Galileo.
I have
no.
suffered enough.
It's
I have
not
recanted
true.
that which I know
have
to be
told
the
you.
truth. The earth moves around the sun.
A dangerous contention. Signor, I am Simplicio, a simple man. Enlighten me.
Simplicio. Oh, I have stared too long at the moon. They're instruments of torture. I do not see too well.
Signor, how can a marble roll along a plank forever? Enlighten me.
Simplicio, imagine this incline were as smooth as the polished silver. I place the marble at the top and release it. What would happen?
It would roll downwards faster and faster until it reached the bottom.
Faster and faster, you learn quickly. Now, starting at the base of the board, will the marble roll upward?
Only if it were pushed.
Then I give it a thrust to send it rolling up the incline. It's motion.
It would slow down constantly, given that the marble's natural tendency is to roll downwards, not upwards, which is contrary to nature.
You declare that on a downward inclining plane a body continuously speeds up, and on an upward incline it continuously slows down. But what would happen to the self-same body placed on a surface with no upward or downward tilt?
Then indeed it would go nowhere.
Not if it were propelled.
Then it would travel in the direction in which it was pushed.
Would it accelerate?
No.
Would it decelerate?
No.
Then at that constant speed, how far should the body continue to travel?
For as far as the surface remained flat.
On a limitless surface, perfectly straight and flat, on the Earth's surface, the body's motion would be perpetual.
Well, yes.
Then we agree. In the absence of friction or resistance, the motion of a body on a horizontal plane is constant. Now, when a body has both horizontal and vertical motion, its path will be a parabola.
But I don't see...
I have proved this. I propel the marble so that it moves across the board this way, while at the same time accelerating downwards. Its curve is a parabola. Now, take note. If I, at one and the same time, propel this marble horizontally and simply release this second one, they reach the bottom at the exact same instant. Thus, the two parts of the motion, the vertical and the horizontal, are independent and distinct from one another.
This is all very well. But how does it reflect the question of whether the Earth moves or not? And if it moves, why the air is not snatched away and the birds left behind?
I have answered your question.
Signor, I am a simple man, merely helping you write your dialogues.
Imagine a ship, a man of war, plowing through the seas. You stand in the crow's nest and you let fall a brass ball. Where would it land?
Behind the mast.
No!
Oh, where then?
It would fall directly beneath you. Motion in two directions, remember, the horizontal and the vertical. Whilst the ball is in your hand at the top of the mast, the ball is moving with horizontal velocity, the same speed as the ship, and that is its motion horizontally when you let it drop. Its vertical motion accelerates as it falls, but it retains its original horizontal motion, the same speed as the ship, so it lands at the foot of the mast.
Well, that's as much as to say that the fall of an object from a moving ship is the same as from a ship that's not moving.
Simplicio! You have seen the light!
What?
Here we stand on a floor that does not appear to move, but we are on the surface of a revolving Earth. We have horizontal motion, and the air stays with us because its horizontal motion is the same as ours, and the birds of the air do not get left behind for the self-same reason. Now, please, do you see?
Yet the heavenly bodies, Jupiter and his moons. And why does our moon not fall downwards?
If I understood the nature of gravity and the role of forces, I have drawn her in detail. I have measured her mountains, but what keeps her there? And the stars in their heavens, forever out of reach? I cannot say. But gravity must be the key.
So, Galileo had solved the problem of the moving Earth. It's very similar to what happened with the moving train. Galileo would have said that when the ball is fired, it pursues its upward and downward motion whilst maintaining the horizontal motion that it had on the train. In fact, taking a parabolic path. But the story is not yet complete. Galileo has rightly separated motion into its horizontal and vertical components. But this was his difficulty. The concepts of horizontal and vertical are intimately tied up with the fact of standing on the surface of the Earth. So Galileo was unable to extend his understanding to the motion of the planets. What was needed was a synthesis to understand motion in any circumstances. The man who knitted these ideas together into a coherent theory was born in 1642, the year that Galileo died. His name was Isaac Newton.
It was in the year of our Lord 1684 that my friend Edmund Halley approached me with a question. What would be the shape of the orbits of the planets around the Sun if the force of attraction to the Sun diminished as the square of the distance to the planet? I was pleased to give him the answer instantly. It is an ellipse, I cried. I have proved it. It must have been 20 years since I had performed the calculations, and when I retraced my steps on paper, I saw to my satisfaction that I had already written down the universal laws governing the motion of all bodies. I had Halley to thank for the publication of my Principia. And I acknowledge my debt to that former giant Galileo, upon whose shoulders I admit I stood. Of course, the Greeks came 2,000 years before him, but the trouble with the likes of Aristotle was that he assumed that the natural state of motion is rest. Whereas my first law of motion states that with no forces acting upon it, a body can be at rest, but it can also move in a straight line at constant speed. This was Galileo's understanding of horizontal motion, but my law is universal. You see, Galileo believed that an object traveling horizontally without friction would go on forever. But for him, this entailed that the object must remain at the surface of the Earth, where it would travel not in a straight line, but in a great curve around the Earth's circumference. Effectively, Galileo was saying that an object could travel thus, but with no forces acting on it. That cannot be correct. According to my law, as it does not travel in a straight line, there must be a force acting upon it. And indeed, there is a force. The force of gravity.
We all know the legend of the apple falling on Newton's head. It was more likely that Newton was observing the moon through the branches of an apple tree and wondering, well, if an apple can fall to the ground, why can't the moon? Then he realized that the moon is falling towards the Earth. I'll go and ask him about it. Sir Isaac?
I had forgotten I was expecting a visitor. Do forgive me, dear lady. My study is the bane of my housekeeper's existence.
I'm sure you have other things on your mind, Sir Isaac. I was wondering if perhaps we might talk a little bit about gravity.
Yes. Thank you. Well, in that case, I would need to expound my laws of motion. Pray be seated. Oh, I beg your pardon. Clutter, clutter, clutter. Motion itself does not require a force. That is the basis for my first law, which goes on, for there to be any deviation from motion at a constant speed in a straight line, there must be a force to cause the deviation. My second law states that the force causes the body to accelerate, but only in the direction of the force. And the acceleration is equal to the force divided by the mass. So, in the case of an object thrown horizontally, it accelerates only downwards, the direction of gravity. The horizontal motion is unchanged, as Galileo showed.
But what about the moon orbiting the Earth or the planets orbiting the sun? How do you explain those?
The moon is traveling here in its orbit around the Earth. Now, suppose that at this point there were no gravitational force acting on it. It would continue in this straight line at the same speed. But observe the pull of gravity tugs it round towards the Earth and causes it to deviate. And here it does again and again, and the motion curves into a closed orbit, an ellipse.
Of course, and that shape, the ellipse, that's due to the nature of gravity, your law of universal gravitation.
Indeed. My law of universal gravitation states simply that any two particles in the universe attract one another with the force of gravity. This force is proportional to the product of their masses and inversely proportional to the square of the distance between them.
Ah, yes, the inverse square law. Sir Edmund Halley must have been pleased with that discovery.
Halley? Why Halley? Certes, it allows me to predict the motions of planets and comets, as much as the tides of the ocean, the path of a stone through the air, the fall of an apple. It enabled me to predict the true shape of the Earth, whose constant rotation requires it to bulge slightly at the equator and to be flattened somewhat at the poles. Did Halley tell us the Earth is not round after all?
Well, it would seem then that your theory is the last word on motion in the universe.
I thought God always had the last word. Have not our laws of motion always arisen to fit the current concept of our place in God's cosmos?
But surely, Sir Isaac, your theory is so successful, it predicts so much and so accurately, it will be difficult for anyone to challenge it.
Dear lady, I do not know what I may seem to the world, but to myself I seem to have been only a boy playing on the seashore, diverting myself now and then, finding another smoother pebble or a prettier shell than the ordinary, whilst the great ocean of truth lay all undiscovered before me.